Thank you all for coming. Today we are very pleased to have Tuan Nguyen trying to defend his dissertation on his work. His dissertation title is Planning with Incomplete User Preferences and Domain Models. As he will tell us in a minute, in automated planning, generally most of the work assumes that the preferences and the dynamics are completely provided and looks at inferring the plans for that. And he's been looking at what if those specifications are incomplete, and he has done some really nice work. He's probably among the first within the ICAPS community to actually, the planning community, to look at these problems, and he's had pretty good success in publishing his work. And I am particularly happy because all of my funding currently is supported by the work that he is doing. The rest of the students are on for the ride. Basically, this is the work that's supporting all of them. And then Tuan actually came to ASU in 2007. He's one of the few students who actually had a paper with me before he came here because his first advisor, I believe, is Min Do, who's right here. And so they have, we all worked together on some work on developing diverse plans, and then so I was very happy when he chose to come here. He came here as a Science Foundation of Arizona fellow, and he's worked continued that work on developing plans under partial preferences, and also has started looking at developing plans under incomplete dynamics. His work has been published in ICHCAI, ICAPS, IIII, NIPS, and AI Journal, and I just checked, he has about 73 citations to the work that he's already completed. In addition to, and so other thing is that both parts of his, several parts of his work is done in collaboration with Min and Alfonso Gerevini in Italy, and Biplav Srivastava in India. And then more recently he also worked with Hank Yusuo. The work that he did with him actually had a publication in ICHCAI and IIII. He's not even mentioning them in today's talk because that's yet another approach for handling incomplete models. So in addition to being busy writing papers and so on, he's also been building up his family in front of our eyes. He got married, he had a kid, and he's now off to start like his life in Boston with both his brand new kid and his wife. So we all, hopefully, if he completes this dissertation defense well, he will be on his way, I believe, in MathWorks, right? He'll be working in MathWorks. One last thing, I actually, the work, Tuan's work, as you'll probably find, is a very interesting mix of formal rigor in developing the models as well as empirical evaluation. And so I think it basically, hopefully will have a good impact on the community. And without any further ado, Mr. Tuan.
Thank you all for coming to my dissertation defense. First of all, I would like to thank my advisors for continuously supporting me and advice, and also his patience for me. I also thank my committee members for spending time with me and give me helpful comments. My dissertation is titled Planning with Incomplete User Preferences, and currently in automated planning research, people assume that actions, so in automated planning research, you are given actions with precondition and effect. The effect can be deterministic or non-deterministic or stochastic in the sense that the outcomes will have probability, and you are given initial situations, a set of low conditions, and you assume that a user, you know exactly what a user wants, and you try to find a best plan, best plan. But in practice, modeling action models or domain models are known to be very costly and easy to make mistakes. And in many situations, we do not know exactly what a user wants. And so there is actually a need for blending with incomplete user preferences and domain models. In particular, about preferences in blending, the traditional view is that we will have the full knowledge of user preferences. In particular, there are two possibilities. The first one is that we assume that there's no preferences specified by the user. And in this case, any plan, so the user is indifferent, any plan is acceptable. The second case is that the preferences are specified completely, and your job is to find a plan that optimal with respect to this specified objective. And either of these two cases, the solution is always single plans. But in real world, of course, the preferences are not fully known, and this can come in two levels. It's completely unknown. So this is the case where you know that the user has some preferences, but she does not specify any of them. Another case is that she will specify some part of the preferences. For example, we know that the user cares only about the travel time and cost, but how much trade-off between these two criteria, we do not know. And so in this case, the full knowledge of the preferences is lacking. The same with the domain models. In blending, the traditional view is that we are given a set of actions fully specified, and even with probabilistic actions, the probability of outcomes are exactly known and specified. This is one example in blending domain where we have a pickup actions that a robot will pick up a ball in a specific room, and in this model you can see that we need to specify the complete set of preconditions and effects. But this, is, of course, is not realistic. And in more practical applications, as I mentioned, modeling completely the domain dynamics is very time-consuming and error-prone. And similar to the case where we have unknown preferences, where we need to revise what does it mean by a solution. In this case, we also need to revise what does it mean by a plan. Intuitively, it will be you want a plan that's more likely to succeed, even if your domain model is incomplete. But how do we define such a solution concept? And we identify three problems, three issues and challenges in blending with incomplete user preferences and domain models. The first one is incompleteness representations. How do we represent the incomplete, the knowledge of the incompleteness? The second one is given this incompleteness representation, what is the solution concept? And of course, after that, we need to devise some techniques to generate plans. So my dissertation has two parts. Preference incompleteness and domain incompleteness, and for each of these parts, I will consider these three issues: the representation, the solution concepts, and the solving techniques. So in particular, for the preference incompleteness, I will consider two levels of incompleteness, as I briefly mentioned. The first one is the user preferences exist, but totally unknown. Another situation is the user preferences are partially specified. This can come with many different formulations. In my work, I consider one particular formulations where we have the complete set of plan attributes that a user is interested in. However, we do not know the trade-off between those attributes. And in this case, instead of generating one single solution, we will generate a set of plans. and I devised many heuristic techniques to synthesize high quality plan set using the quality measure that I will describe here. In the case of domain incompleteness, again, it can come with many different forms of incompleteness representation. For example, in MVP, this can be a set of probability for transition functions. In my work, I look at incomplete domain in deterministic environments. In that, in my formulation, actions can have possible precondition and effect. In addition to precondition and effect that you already know. And optionally, the domain writer can specify some weight on the likelihood of some particular possible precondition and effect that can be realized during the execution. For solution concepts, I introduced a robustness measure for plans given these representations. And again, solving techniques, I consider heuristic different approach for synthesizing robust plans. In my proposal, as you may remember, I already talked about this part, preference incompleteness. In particular, I introduced the distance measure for a set of plan based on the base level feature of plan like action, state, or causal link. I work on a CSP-based and a local search-based planner to generate a diverse set of plans using this measure. And this is for the case where we do not know anything about the user preferences. In the case of partially specified, I use a measure called integrated preference functions that were used before in scheduling, and I use this measure for planning, and I work on some approaches to generate a set of plans given optimizing this measure. These are the sampling approach, ICP heuristic, and the hybrid combining these two. This approach was built on top of stochastic local search (LPG). And so this is a list of publications that I have for the preference incompleteness. I published in ISCA 2007. One version, one is in 2009, and we combined these two papers in the AIJ's 2012. And for the domain incompleteness, this is the paper where we first introduced the notion of plan robustness. So before this, in 2000, Gallant and Lesch, I believe, was the first to introduce incompleteness in a deterministic environment. However, the quality of plan in their works are determined by 4 different types of risks, and it doesn't have good connection with the probability of success in the plan. And this was the first. We first introduced the robustness measure, and in these two papers, we introduced 2 approaches to generate robust plan. The first one is compilation, which we compile the problem of synthesizing robust plan into conformal probabilistic planning problems. In this most recent approach, we consider a holistic approach to generate plans, which is much more scalable than the compilation approach. And so, because I already talked about this in my proposal, in my presentation today, I will focus on these new things. Okay, so first of all, I want to review a little bit about strips, which is the simplest domain models. And what is complete. So we give an intuitive what is the complete domains. So in this complete domain, you are given a set of predicates. This is complete. This is the set of features that you want to capture. You want to capture in your environments, and you have a set of complete operator where each operator will have a name. In this example, we have an operator pick up an object X, and we have a set of complete set of preconditions telling you the conditions at which this operator can apply. And so in this case, in order to pick up an object, the hand of the robot needs to be empty, and the object is clear, meaning that there's no object on top of it. And after you execute this operator, the effect will be that the hand of the robot is no longer empty, and your hand and the object is being whole, and the object X is no longer clear. And so this is a complete set of proposition. And so this is a single complete model. And planning problems in strips in these complete models is that is given you are given a set of type objects, and so together with the predicate set mentioned above, we will have a set of propositions, and together with the set of operator, we will have a set of grounded actions. So these actions are of course complete, and we are given an initial state and a set of role conditions. And what we want is that we want to find a plan pi that achieve the goal starting from i's. And of course this is based on the definition of transition functions like this. So in particular, if we are in the current state S and we execute an action A, the next state will be S union with all the new feature that this action will provide, and delete all the feature that this action delete. And this happens only if the precondition of action A is justified. Otherwise, the next state will be undefined. And so a replanning process needs to be triggered. And a transition function for a plan can be at a given state can be defined recursively. Okay, that's the incomplete models. So what is incomplete domain models in our formulations? I assume that we have a complete set of features, however, the set of operator is incompletely specified. In particular, each operator will have a name, preconditions, a set of known preconditions, and a set of known effect. But we also have a set of possible preconditions and possible effect. In this example, I extend the predicate set in the previous example to introduce light and dirty as two new features. And in this example, if we do not know the conditions of the arm of the robot, then the robot can only pick up an object which is light. And so I can specify that as a possible preconditions. And similarly, if I do not know if the robot's arm is dirty or not, one possible effect is that after I pick up an object, the object is become dirty. So now one important thing I want to mention is that incompleteness in deterministic domain like this is very different from stochastic domains, in the sense that if the first time you pick up an object you fail, then the next time you pick up it you fail also. But in stochastic domain you can try to do that multiple times and increase the probability of success. And the incomplete domain is defined by these two pairs. Notice that the annotations here, the possible precondition and the effect, are specified at the schema level. And if we have if we have k these annotations, we will have 2 power k possible complete models. One of these will be the 2 models, but we do not know. Only until we execute the plans. Planning problems with incomplete domains. Again, we are given a set of type objects, and again, together with the predicate set, we have a set of grounded propositions and a set of grounded actions. But these actions are incomplete, meaning that they can have a set of possible preconditions and possible effects. However, because the annotation are specified at the schema level, 2 different grounded actions instantiated from the same operator will be realized similarly. And we are given an initial state and a set of goals, and we need to find a plan pi to achieve G starting from I. But what does it mean by achieve a goal G, given that our domains, our actions are incomplete?
Is the initial state complete?
Yes, it's assumed to be complete. So this goal achievement is ill-defined, and so I need to revise this definitions. But first of all, what is the transition function in these incomplete domains? So intuitively, given an incomplete domains, when we apply an action an action sequence pi in a state S, we will have a set of possible states depending on which complete models are the true models. So here we have the union of gamma di, where gamma di is the transition function for the complete models di.
So you know the definition of these, what the complete model should be, in order to get these numbers here.
Which number can you?
No, these operations. How much do you know about the model? Set of possible states. How do you know that?
We know the set of possible prediction and effect.
Yeah.
And we cannot list all the complete
Oh,
models.
list down. Okay.
You cannot.
Okay.
Yeah. But this is just a
If you go back to
definition.
the slide, couple back. Yeah. So if the possible precondition is light X, so you're assuming that either is light X or not light X,
Yes.
one of those 2 possibilities,
Yes.
and similarly possible effects, one
Yes.
of those.
Yes.
So that's what.
Yeah. That's
So my question is, cannot this be incompleteness brought it down to the level of the initial state?
Yes, that's actually one of the approach that we consider compilation, where we compile this away. So
To the initial state?
yes.
Okay.
So the
Because there's a lot of work on that kind of planning.
yeah. Yeah. I will go to that.
That's fine.
So the definition of transition function given the incomplete models is defined based on the transition function given a complete domain DI. And given this definition, the probability of ending up in one state S params after you execute pi is computed by this, where you sum up all the complete models, where after you execute that plan, that action sequence, given that complete models, you end up in S.
So this is, how do you know this probability? Are you assuming equal likely or what?
Currently, in my work is you can put some weight on on this, just because I will move to that weight later.
Yeah.
So currently it is equally likely,
Okay.
but in the
So
more
that
general
means,
form,
that means you do have some type of model behind you, that equal likelihood model. That's
Yes.
they're equally likely. You have a model that says it's equally likely, all of these. Dirty, not dirty is equally likely.
yes, if you do not specify any
Okay.
likelihood. And now, in order to define the transition function given a complete model D, I consider two different executions for an actions. The first one is I call strict executions, where given a state S, you execute an action A. We will have this resulting state if the preconditions of this action in the complete domain D justify in S. Otherwise, we will go to a dead end state. This is strict execution. Another execution semantics that we consider, we call generous executions, where when actions fail to be applied, meaning that its preconditions does not satisfy, then the next state will stay the same. So these executions will give more opportunity for the planner to insert some action into an existing plan to increase the robustness of the plan.
So the generous one, if the precondition is not satisfied, then
the next stage is the same
as
in the
before.
curve. Yeah.
And the strict one
It's
is what different?
undefined. So here is an example. So in this example, we have a set of three propositions, P1, P2, P3, and in the initial state we have P2 are true, the other two are false, and we want in the goal, we want P3 is true. And assuming that we have two actions in the domain, A1, A2, where I didn't write the specification of A1, A2 here, but we can see it here. So the dashed line here means that A1 has a possible precondition P1. The solid line without the minus means that A1 has a certain end effect and a certain two certain end effect P2 and P3. Action A2 has a known precondition P2, one possible elite effect P1, and one possible end effect P3. And so totally we have three possible precondition and effect in this domain. And so we have candidate complete models. And for each of these complete models, we can easily check whether this action sequence actually achieve the goal or not, according to each execution semantics. So, for example, in these third complete models, A1 has P1 as a precondition, but P1 is false initially, and so according to the strict semantics, this plan immediately failed. But in the GE semantics, the plan can continue, and because of that, A2 can execute, and eventually this plan will succeed because it's achieved the goal. And so from this example, it's quite intuitive for us to say what we want about robustness measure for plan. Naturally, we will prefer a plan that succeeds in as many complete models as possible. I haven't introduced any weight. And in this particular example, oh, I have a mistake here. So the robustness for GE in this example is 6/8, and for SE is 4/8. And in general, the robustness, according to strict execution, is always less than or equal to that of plan in the generous executions, because any plan, if it succeeds in strict execution, also succeed in other execution semantics, but not vice versa.
Do you incorporate any kind of observations or sensing into this?
No, this is I don't have sensing in this way.
Because, I mean, if I think of the realistic scenario, if you don't know things, after you do some action, you observe
Yes,
what's happening, so that way, and because there's no non-determinism, it's only lack of knowledge.
Yeah.
By observing, you can fill up some of the
That's
things
right.
that you don't know.
Yeah, that's okay, a little bit more general. As you mentioned, we also allowed the domain writer to specify some weight on how she thinks that this possible precondition of effect will actually be the real one. and the robustness measure will be generalized as this one. This is a summation of all the complete models under which the plan achieved the goal. So this is no longer a uniform distribution. Okay, so next I will talk about two problems related to planning with incomplete domains. The first one is that given a plan, how do we compute the robustness value of that plan? I will introduce a method to reduce that problem to weighted model counting, and I also show that actually the complexities are the same. And then I will consider two approaches to synthesize robust plan compilation and a heuristic search approach. So for the plan robustness assessment problems, one way to do it is that we can, given a plans and given incomplete models, we can construct a set of correctness constraints for that plan type. This correctness constraint will make sure that the state transitions caused by actions are correct, and eventually the goal will be justified. And after we have this set of constraints, the weighted model count of this set of constraints will give us the robustness measure. So this is one example for, actually this is the full set of correctness constraints for a plan given the, according to strict execution, meaning that all actions, precondition and possible precondition need to be justified. And eventually the goal needs to be justified too. And so these are the set of correctness constraints, and I can briefly go through. For example, here, this one is the establishment constraints for the known preconditions of an action AK. So in your plan, you have an action AK where P is a known precondition of that actions, and if you see that the value of P is false in some reverse level, so you must enforce this constraint, saying that one of the actions in the in between having P as a possible act need to be realized. As a real act effect. Otherwise, this action will fail. Sorry, I should say that P is a known precondition of an action AI. AK is the index. And similarly, this second constraint is the establishment constraint for possible preconditions. So this part is similar to this, but we have this antecedent because we only need this if P is actually realized as a known precondition of this action AI. The first constraint is a protection constraint for known preconditions, where if I see some actions AMs having P as a possible delete, and AM realize and AM actually delete P, then some of the action after that need to re-establish P. And similarly, the fourth constraint is for protection of possible preconditions. This part is similar to this, but we need this only when P is realized as a known precondition. Okay, we can call weighted model counting of this set of constraints, and this will give us the exact robustness measure. But that doesn't mean that the problem of computing plan robustness is as high as weighted model counting. In fact, I proved that is indeed the case. I show that the problem of computing robustness measure for plan pi is sharply complete. So this is the class of problems. When one problem belongs to this completeness class is that you need to you are given a set of Boolean formula, and you need to count the number of justifying assignment. So obviously it's at least as high as NP complete. And the reduction is that I start from a monotone to SAT problems, and I introduce an instance of the robustness assessment problems with an incomplete domain, a blending problems, and a blend. And I show that the weighted model counting and the robustness of that blend is the same. Okay. For synthesizing robust blends, we consider two approaches. The first one is compilation approach, as Chita just mentioned, and the second one is heuristic search approach. So for the compilation approach, intuitively we see that the realization of possible prediction and effect will be determined by some unknown variables, right? And so we can compile away the domain incompleteness using conditional effect, which says, for example, if this variable, this is the unknown variable, is true initially, then P must be a prediction of A. And so the domain incompleteness will be turned into state incompleteness with complete domain. And in blending, we have blending problems called conformal probabilistic blending problems, where the initial states are uncertain, is uncertain, and actions can have probability. And in this, this is one example of the pickup actions. For example, the first case here is that if this unknown variable is true, then this one is true, then you need to have the ball need to be light in order to for this one to be this conditional effect to take place. And in my paper presented in NIPS, I introduced this compilation approach, and I also test this approach with the current best blender for probabilistic FF. And these are some results I have on my.
What is M?
M is the number of possible prediction and effect. So 2 power M is the number.
So you're basically, you enumerated here. When you go back and do the compilation experiment,
yes,
you're enumerating all
you need to enumerate.
Okay.
Yeah. And one of the consequences is that
Of course.
is fail with large problem instances.
So what is the first column? The P probability of what?
Oh, this is the probability of achievement. So this is the goal probability that because probabilistic FF require to achieve the goal with at least that probability. And this is the blend length and the limit times.
So when you can you go back to that table? So when there is no result, it means that the planner cannot find a plan within the allocated time.
Yes, this is failed. This cannot find blends. And I see many cases where I know for sure that a blend succeed, but the prop FF just run forever.
What was
your timeout?
The timeouts, I believe, in 15 minutes.
So it's kind of interesting because when the problem becomes more complicated and you require the probability of achieving the goal to be higher, the FF actually run faster. When with the larger M, then basically it makes it like there are more possible domains model, right? And at the same time, you require the plan to achieve a higher probability of succeed.
Because in order to when you have a higher row probability requirements, then some action need to be put in order to increase the robustness.
So I'm just trying to see how it affects the probabilistic FF performance. So it's basically narrow down the inference within probabilistic FF, make it search for a smaller set of possible plan, and that's why it helps you find a plan faster, or
I'm not sure I understand.
because when M is smaller and
Smaller.
and
For
P is
example-
smaller,
For example, here.
yeah, then MF fails more frequently than when M is higher, given the same problem, right? And with the same running time cutoff.
Yes.
So I'm just trying to see intuitively how it happens.
Yeah, one observation I observed, for example, when I test with prop FF is that even in some instance where I have only one possible preconditions, and I know for sure that the plan is this, prop FF just failed.
Okay.
Yeah.
I'm
I
just
guess because the relaxations inside prop FF is too much. It's not only relax the possible it's not only relax the delete effect, but also relax the preconditions.
okay.
Randomly choose only to keep only one precondition.
Okay. Yeah.
So double relaxations. And one observation by other people is that when you change the order of the conditional effect inside in prop FF, behavior will a little bit will be changed.
So I'm wondering whether this part of his question is, I think the failure that you're showing is two different kinds of failure, isn't it? I mean, if it fails to find a plan versus if it ran out of time, you distinguish in that table. Because what happens with m equal to 1 is, as I keep increasing my robustness requirement, there are no plans that will actually satisfy. I mean, there is no plan I can construct, so you're guaranteed to fail. I mean, so upfront. So that, I mean, I think that his point is, what he's pointing out is that it sort of is unintuitive that for m equal to 1, you are unable to solve at 0.4 level, whereas for m equal to 5, you are able to solve at 0.8 level. It would make sense if in fact that not being able to solve is not because you ran out of time, but also because there is no plan. And that is actually I believe that's what actually happens there. You have, with just one hand, there's only so much robustness you can provide.
So in this domain, is this guaranteed to be complete, and you can find that if there is no model, then you can determine that?
Yes, the plan can tell that is
So
if the heuristic fail, then it's switch to complete search.
And you're using the GE model, not the SE.
Yes, this is GE model.
Okay, that makes a little more sense here.
Yeah, because in GE models, so in this domain we have multiple robots. If multiple type of robot, and if one type of robot fail, then other type of robot can be put in to increase the robustness. And that's why the length will also increase. Okay. The next approach that I consider for synthesizing robust plan is heuristic search approach. First of all, the first thing I want to do is that even though I already have the definition of transition functions previously as a set of state, I do not during the search I do not maintain explicitly this set of resulting state. However, instead I maintain a set of what I call approximate transition functions, which give me a set of propositions instead of a set of state. And this approximate transition functions can be defined as follows. Given S is the current state, we execute action A, then the next state will be S plus some known end effect and some possible end effect, and we remove all the known delete effect, but we do not remove any possible delete effect because that might not happen during execution. And the conditions for applicability of this action is that the known precondition needs to be justified. We do not use the possible precondition here. And the definition for the whole action sequence is defined recursively. And with this approximate transition functions, in my thesis I also show that any solutions in this in the complete model, which we do not know, it still exists in the solution space of our approach. So that is complete in that sense. It's sound in the sense that for any plan that returned by this particular approximation functions, there is one complete model under which this plan succeeds. But that complete models, of course, may not be the real one, and so plans still fail. So my planner is an anytime planner where initially delta is a robustness threshold. Initially is 0, and I repeatedly try to find a plan pi such that the robustness of pi is greater than delta, and then I update delta with this new robustness. I will do repeat this until time bound reached. In my experiments, I use 15 minutes. And the last plan is the best plan that I can find. Okay. Given that computing the exact weighted model counting is and the exact robustness is hard. In my approach, I use two approximations, one upper bound and one lower bound during the search. And the upper bound is used in order to check whether this is used to reduce the number of times that I need to call the exact weighted model counting. So whenever I see a state where the upper bound is of the current plan prefix is greater than the threshold, I call the exact weighted model counting, otherwise we don't call. And I also have a lower bound on the exact robustness, and it is used as follows. So during the search, I need to quickly estimate how far I am from the current state S to a goal state, given the current robustness threshold. So this is the my estimation, and in order to compute this estimation, I need to construct in planning we call a relaxed plan. So in this picture, pi k is a plan prefix with k action, and to the pi is a relaxed plan. And I need to find a relaxed plan where I want the exact weighted model counting of sorry, I should put the sigma here. Of the correctness constraint for this plan prefix concatenate with this one, the exact weighted model counting needs to be greater than delta. But to avoid the exact weighted model counting, I use only a lower bound. So I try to look at the relaxed plan pi to the pi where the lower bound of this is greater than delta. Of course, this will make the plan incomplete, and it's incomplete anyway, given the search that algorithm that I chose, which is stochastic search. So how to compute these two approximations? Remember that I show you that this is the set of correctness constraints for given plans, right? and I color these variables with two color, the red and the green. So the red variables, we can see that in these constraints, the variables that corresponding to possible regression and possible VID always appear on the antecedent, right? And the variable corresponding to the possible F will be on the right hand side. So we can turn this constraint into clauses where the variables for possible regression and possible VID will appear in the negative form only. And so we can consider this as a set of clauses with positive literal only. And of course we need to change the weight for this. The weight of this one will be 1 minus the weight of the variables. Given that property, we can show that given two positive clauses, the probability of two clauses C and C prime, the probability of C given C primes is at least the probability of C, because these give only positive interactions. And so, given a set of constraints for pi is C1 to Cn, the exact weighted model counting of this is pi is the probability of all of this, the conjunction of this, and based on the chain rule, we have this, and we apply this. We can see that one law bound we can use is the product of the probability of all the individual clauses, and this can hold when clauses are independent. For the upper, bound, one trivial upper bound we can use is that we can just take the mean of the probability for individual clauses. But we can do much better by observing that the clauses only contain variables corresponding to one specific predicate. And so this set of clauses are highly decomposable. And I maintain them as a set of connected components. And for each component, I will take the means of all the clauses in each component and multiply those means. And so we have a better upper bound. So that are the two bounds that I use. The last piece in this approach is how to extract a relaxed plans such that the concatenation of the plan prefix and the relaxed plan, the low bound of that is greater than delta. And so there are three steps. I need to build what we call relaxed planning graph. There is a structure we use in planning to extract relaxed plan. And in this relaxed planning graph, I ignore all the known and possible VID effect. Clauses can be will be propagated for proposition and actions in the same quite similar idea with the label uncertainty graph. And after that, I will extract the relaxed plans. Also consider the low bound on the robustness. So, in order to construct the relaxed planning graph, will the first layer is the proposition layer, where this is the state, the state after the plan prefix, and each proposition here Pj will be associated with a set of constraints. Where is this constraint? This constraint can be established based on the correctness constraint that I mentioned before. The next is the action layer. So we are here at the action layer AT, and before that we have a proposition layer LT, and this action layer will contain all the actions that can whose known prediction justify this layer, and And the set of constraints associated with these actions will be determined based on the set of constraints of its known precondition and possible preconditions. And I also have, for each proposition, we also have what we call no-off actions to maintain this proposition across layer. And so the no-off action will have the same set of constraints with each corresponding propositions. And for the next propositions, this will be the set of propositions where this is added or possibly added by some action in the previous action level, and the set of constraints associated with this proposition is computed looking at actions that possibly added, certainly added or possibly added, and then take the constraint of these actions combined with the set of constraints for the blend prefix, because the blend prefix actually provide a prior for this constraint. And I quickly compute the lower bound and choose the ones that give me the best lower bound. And that will become the set of constraints for PI here. And this also will give me the best supporting actions later on when I extract the relaxed plan. So in order to extract the relaxed plan, this is an overview. So here we have a relaxed planning graph with proposition layer, action layer, proposition layer, action layer. We start from the goal. I assume here we have only one goal G, and we will choose the best supporting action for G at layer T. This will be computed, as I just mentioned, based on this max operator. And the subgoal PA and P6 will be put into a queue with, of course, with the action A phi, and also indicating that PA is non-deletion and P6 is a possible deletion. And assuming that the next subgoal will be is PA, then this process continues until we reach the first layer in the relaxed planning graph. And so, in order to construct the correct constraint for the relaxed plan, I always totally order the actions in the relaxed plan. And the relaxed plan extraction will succeed when two conditions happen, all known preconditions are supported, and the low bound is greater than threshold. So one question is when to insert an action, because here actually I need to balance between the robustness and the reachability, and so a supporting action is inserted only if I need it. I will quickly explain this, but it depends on two things: the relation between the subgoal and relaxed plan state, and the robustness of the current relaxed plan and that relaxed plan if I insert this supporting actions. And here the relaxed plan state is, I show it here. So this is a current relaxed plan, and right before every action in the current relaxed plan, I define a set of state, a set of propositions. This is the set of propositions that is known to be true or possibly true. I keep the set of propositions that are known to be true separately, because this will help me a lot later on. And there are six types of relation between the subgoal and the relaxed plan state. So here we can see that P is a known precondition of A, and in this case P is outside this relaxed plan state. In this case P is inside this state. In this case inside and even in the known set of known propositions. Similarly for the possible preconditions. Okay. Now in the first case where P is a known precondition and outside the relaxed plan state, this means that there are no action in the current plan prefix and the relaxed plan that is currently supporting this subgoal. And so I immediately insert the supporting action into this relaxed plan. And actually this is the type of subgoal will make the relaxed plan incomplete, meaning that if your relaxed plan has this one unsupported, then the robustness for sure will be 0. In these three cases, for these subgoals, the first case is P is a known precondition, but is here in the relaxed plan state, but it's outside the known, the set of known. And similar for this one and this one. So in this case, you do not need to insert any actions. You don't have to. So I only insert if after inserting that that supporting actions, the approximate of the plan prefix plus the relaxed plan, the new relaxed plan increase compared to the previous one. Otherwise, I do not need to insert. This is the way that I balance between the robustness and the reachability. And there are two cases where we do not need to do anything, where in this case P is a known precondition of A, and it is known to be true. And so we don't need to insert any supporting action, and similar for this one. And that is about relaxed plans, which will give me an estimation of how far I am to the goal, given the current robustness threshold. One last piece I did is a search algorithm, and in my work, I intentionally choose a stochastic local search with tail-bounded restart in Identium by Andrew Cole. The reason I choose the stochastic local search is that by using this, I can avoid checking the duplications of the leaf state, which is very expensive. For example, in probabilistic FF, that planner actually need to call a sequence of SAT solver to check some sufficient condition of whether two belief states are equivalent. And so this search algorithms, let's say this is the current state where we have the estimation 100 action away from a goal. So this one, I will probabilistically sample some actions, and I select one of them, and then I will go execute that actions, go to the next state and do it again until I find some state where the estimation is better. In this example, 55. Otherwise, I will, if the bound reach, I will come back to this state, and I do that until I reach an estimation which is 0. In this case, the goal is achieved. And so I implement this approach, and I test this approach with some domains here. So I take a complete domains in